For the homework solutions to the Chapter 13 homework, which is due on April 1st. No fooling. And I remember I did a couple examples in class with universal gravitation as well. So P4 was asking about, says that the International Space Station is 300 kilometers above the surface of the Earth. What's the gravitational force on a 1 kilogram sphere? So you got to use table 13.2 for lots of these things. So that's the radius of the Earth. That's the altitude, which is 3 times 10 to the 5th meters. So the total distance is 6.67 times 10 to the 6 meters. So I can think of a 1 kilogram object and the mass of the Earth, which is also in that table 13.2. Come up and I get around 8.95 newtons. For problem 13, it says planet Z is 10,000 kilometers in diameter. The free fall acceleration is 8 meters per second squared. What's the mass of planet the unknown planet? So acceleration on the surface of the planet is equal to the gravitational constant, big G, times the mass of a planet divided by the radius squared. So I'm rearranging that to solve for the mass. So that's 3 times 10 to the 24th kilograms, which is about half of the Earth. And then the next part of the question says, well, what's the free fall acceleration 10,000 kilometers above planet Z's North Pole? So there's a couple things you could do here. It did say that the planet was 10,000 kilometers in diameter. I immediately realized I needed radius because that's the distance to the surface. So I did change that up here from what was given. But now the satellite is 10,000 kilometers or 10 million meters above the surface of the planet. I need to use the radius of the planet plus that distance, which is 1 times 10 to the 7th meters. So get the acceleration that way, gm over r squared. It's about 0.89 meters per second squared. Conceptually, you could have used proportions to figure this out. So the distance is 3 times as far away as the planet's surface. The acceleration is 1/9 as much. I do not know why I did not write the word surface there. So we will do something like that. Probably won't show up on the PDF, but at least if nothing else, we'll make it nice and green so that way it'll sort of match. Okay. Yeah. So 1/9 as much because it's 3 times as far away. Problem 15, the escape speed from Jupiter. Well, I derived the formula for escape velocity using energy in class. We did that the week before this. So that's radical 2 gm over r. So the mass of Jupiter and the radius of Jupiter are given. For some reason, they used slightly different radius for Jupiter and got a slightly larger answer. This was from table 13.2, so around 59,500 meters per second. For problem 20, what was asking is, you're visiting a distant planet. You determine the planet's mass twice that of the Earth, and the free fall acceleration is 1/4 as large. So what's the planet's radius? So I'm thinking Earth is basically the free fall acceleration is 10. So I'm thinking of the universal constant as 1. I'm going to call the mass of the Earth 10 and divide it by the radius 1 squared to give me something that equals. So if g on the planet is 1/4 that of the Earth, then that's be 2.5. We know the mass is double that of the Earth, and so we're trying to find the radius. So 2.5 equals 20 over r squared. R squared is equal to 8. R is equal to 2.8. So the radius of the planet is 2.8 that of Earth. Multiplied that by what's given in table 13.2, and I get 1.8 times 10 to the 7th meters. To find the escape velocity, do basically what we had done here. Now we know the mass of the planet, which is double Earth. We know the radius, we just calculated that. So I end up getting 9,400 meters per second. Problem 24, I like this because it's proportional, it's conceptual, there's not numbers in it. Well, there are a little few numbers. But essentially the picture is helpful. So you've got 3 satellites orbit a planet of radius r, and and that's shown in the diagram. Satellites S1 and S3 have a mass of m, satellite S2 has a mass of 2m. Satellite S1 orbits in 250 minutes, and the force on S1 is 10,000 newtons. So the diagram shows S1 and S2 are at the same distance. That's twice the radius of the planets, and satellite 3 is 3 times the radius of the planet. So you're asked to find the periods of S2 and S3. Well, the period for S2 is going to be 250 minutes because that's the same distance as S1. The period for S3, you have to do a decent chunk of math on. You could use Kepler's third law, which is in the book. I find that really tough to remember. So the orbital velocity is equal to radical gm over what? Basically, this is 1.5 times as much as the other satellites. So essentially, the orbital velocity would be 0.816 as fast as S2 and S3. So the distance to orbit is 2 pi r. Well, that's 2 times pi times 1.5 times the radius. So essentially, I get the velocity, which is 0.816, is equal to 1.5 times as much over the time. And then I'm rearranging that to solve for the period of time, and I get 1.837 times as much. So 1.837 times 250 minutes is 459 minutes. So I did this kind of a circuitous route. Again, you could have absolutely done this proportionally using Kepler's third law. For the forces on S2 and S3, well, essentially it says the force on S1 was 10,000 newtons. S2 is the same distance but has twice the mass, so that would be 20,000 newtons. S3 is the same mass, but it's 1.5 times as far away. So since the force is inverse related to the inverse square of the distance, I take that 10,000 newtons divided by 1.5 squared. So that's 4,440 newtons. For C, looking at the kinetic energy of 1 related to the kinetic energy of 3, remember, kinetic energy 1/2 mv squared. Well, the mass of these is the same, so we're really looking at the comparison of the velocities squared. So the velocity of the first one was 1 squared. I had kind of figured out the relative velocity up here was 81.6% or 0.816 times as much. So 0.816 squared is 0.6659. So a ratio of 1 to 0.6659 is equal to the ratio of the kinetic energies, and that's 1.5 to 1. So the object that's basically 1.5 times as far away has essentially 2/3 the kinetic energy. The closer to the further satellite has 1.5 to 1 times as much kinetic energy. So that was kind of interesting. I didn't know that. I guess it kind of makes sense. I'm not sure if it makes sense to me yet. So for problem 33, NASA would like to place a satellite in orbit around the moon. They want to have it remain at the same position over the lunar surface, so that is a geosynchronous satellite. Want to find the satellite's altitude here. So this is basically an orbital velocity is radical gm over r. The mass of the moon, the period of time for the moon are given in table 13.2. I converted that to standard units, which is seconds. So essentially, again, I'm using what I did in class on Monday. The orbital velocity 2 pi r over t is radical gm over r. So this is a derivative of Kepler's third law. And I know everything about the moon except that radius. So I'm solving for r. So essentially, r cubed is equal to this large number, which is 6.9 times 10 to the 23rd. If I take the cube root of that, that's 8.84 times 10 to the 7th meters. Well, that's the distance from the center of the moon. So to get the altitude, I have to subtract the radius of the moon, which is 1.74 times 10 to the 6 meters. So this would be the altitude, 86,700 meters or 86,700 kilometers, which is a heck of a long way from the moon. I think that's almost a quarter of the way to the Earth. So I'm not sure if this is realistic, because I'm not sure if the Earth's gravitational pull would have a significant effect at that point. At any rate, the things I got from table 13.2, I've got these red asterisks by. Problem 41 is asking about an object of mass m is dropped from a height above a planet of mass m and radius r. Find the expression of the object's speed as it hits the ground. So essentially, this is a conservation of energy problem. You could think of a near planet approximation, but it would give you a slightly different answer. So I think initially the object as it's dropped isn't moving, it has zero kinetic energy. As it's dropped from that height h above the radius of the surface, the potential energy is negative gm times the mass of the planet over r plus h. Just before it hits the ground, the kinetic energy is 1/2 mv squared. Just before it hits the ground, the potential energy is negative gm mass of the planet over just r. So the mass of the falling object is in all three of those, and so essentially I can cancel that out. And if I basically rearrange and solve for v, it's messy. I got this and left it there. The textbook showed a couple other algebraic solutions. I would have screwed that up, I think. I mean, I think I know how to do it, but it's very annoying. So like I said, I would have stopped there. Chapter 13, problem 45. I think what you need to do is recognize in this particular case what it's, hold on for a sec, it's asking you can jump straight up a distance of 45 centimeters. Asteroids are made of materials with a density of 2,800 kilogram per cubic meter. What's the maximum diameter of a spherical asteroid? So you can get by jumping. So the first thing is find the speed of the jump. Well, your initial kinetic energy, just as you jump, is going to equal the gravitational potential energy at your maximum height. So that's m times g times 0.45 meters is 1/2 m initial jump speed squared. So I get the jump speed is around 2.97 meters per second. Now, the tough thing here is I want to find the escape velocity, right? And I need to find the radius of that asteroid. So 2 is fine, capital G is fine. Mass of the asteroid is not easy. So I have to remember that density is equal to mass divided by volume. So mass is equal to density times volume. Well, the density was given. This is the volume of a sphere. So essentially I get that the mass is equal to 11,729 times r cubed. So essentially I am finding that escape velocity, which is 2.97 meters per second, is equal to the square root of 2 times g times 11,729 r cubed over r. One of the r's cancel out. So I'm rearranging all this stuff. And so at this point it's just an algebra problem. I squared things on both sides, so I've got v escape squared equals 2g mass over r. Again, one of the r's cancels out, and I end up getting a radius of 2,374 meters multiplied by 2 to get the diameter around 4,750 meters. So that was a little annoying. You had to understand the density and the volume of a sphere. Number 50 says a 4,000 kilogram lunar lander is in orbit 50 kilometers above the surface of the moon. You need to move it to a 300 kilometer high orbit in order to link up. So how much work must be done? I think here the easiest thing to remember is the total orbital energy at both distances. And so you could do this a pretty complicated way, but for a circular orbit, I said this was useful to know. The total mechanical energy is negative 1/2 of the gravitational potential energy. So this cut off the mass of the moon. So that's 7.34, I think, times 10 to the 22nd kilograms. So at R1, you've got that height plus the radius of the moon. At R2, you've got that height plus the radius of the moon. So essentially, the total mechanical energy at R1 was this. Total mechanical energy at R2 is this. It's closer to 0. It's not as negative. So the work is equal final minus initial energies. That's a positive number of joules. So to move it up to a higher altitude, you have to do positive work on it. and that's around 6.7 times 10 to the 8 joules. So hopefully those help. I think, honestly, the first half of the problems aren't bad. I think getting to some of these mathematically a little bit tougher, but a lot of things you can solve proportionally. This one with the, I think was a mess, but it was good showing you how to derive a formula, starting off with conservation of energy. This one, the density thing, was a little out there, but again, it's something where I don't think that's on your formula sheet, so I don't think you'd have to know that.